lesson on indicators for rust. The aim today, well, you need to be able to write the ion electron equations for iron rusting so that you will be able to state the indicator used to detect rusting and state which ion it detects. Additionally, we will reinforce the fact that when OH- is present, it makes a solution alkaline and can be detected using an indicator. So, what is corrosion? Can you remember the definition of corrosion? Pause the video and see if you can say it. Well, corrosion is the oxidation reaction that occurs on the surface of a metal, turning the metal atoms into metal ions. So what's going on with iron? Well, the key to writing out the ion electron equations and understanding what goes on with iron, you first need to remember what rusting is. Now, rust that forms on the surface of a metal is actually Fe2O3. It's the chemical compound where there's 2 ions to every 3 oxygens in that ratio. Now, what does that mean? Well, that means that our iron in Fe2O3, because we do the crossover method to get this formula, we had at the end 2 ions and 3 oxygens, so by using the crossover method backwards, that means that iron must have a valency of 3. Oxygen, well, it's always going to have a valency of 2 because it comes from group 6 in the periodic table, and so therefore its valency is always 2. So we know that iron is going to start as Fe and then become Fe3+ when it exists as iron in rust. So at the end of our story, we will have Fe3+. Now, so at the start, we've got iron, as explained. It rusts, and eventually it'll form Fe2O3, which will become Fe3+. Now, there is 2 equations, so therefore there is 2 steps to get there. So how do we get there? Well, the Fe, first of all, because it undergoes corrosion, corrosion is an oxidation reaction, and oxidation is the loss of electrons. Well, the iron must lose electrons, and in fact it does. It loses 2 electrons to become Fe2+. So iron, at the start, loses 2 electrons when it rusts to make Fe2+. But remember that the end of our story is where we have rust, which is Fe2O3, which contains Fe3+. So, chapter 2 begins with Fe2+, changing into Fe3+, and how does it go from 2+ to 3+? Well, it becomes more positive because it loses an extra electron. Now, these are the 2 equations that it's helpful if you remember them. It's not hard to remember if you try that strategy that I have taught. That if you think of the start of iron before it's rusted as Fe, if you think that it forms Fe2O3 and becomes Fe3+, it changes by losing 2 electrons to become Fe2+, and it loses an additional electron to become Fe3+. Now, if you don't want to remember them, they are available on page 10 of the Chemistry National 5 data booklet, so you could just look them up. But the problem with just looking them up is that there is an additional iron equation on page 10, so therefore there is the chance that you would write the wrong equation down. So I advise thinking of the equation like a story, where you've got the start of the story, the end of the story, and how to get there. Now, what will have to do with an indicator for rust? Well, the indicator for rust is a ferroxyl indicator. Now, it does contain potassium hexacyanoferrate 3 and phenolphthalein, but you do not, for the National 5 chemistry exam, need to remember that fact. Okay, you just need to know that ferroxyl indicator turns blue in the presence of Fe2. Okay, for the exam, you need to state the colour change. So you must state that it changes from a yellowish green colour to a blue colour. Now, you may have noticed the pink in this diagram. It's not, in real life you would not see any pink, or at least I have never, whenever carrying this out, seen any pink in the chemical reaction. However, I am going to explain where that pink has been shown in this diagram. So why the pink in the diagram? Well, before we start that one, let's see if your short-term memory works. Can you finish those equations? Pause the video just now and see if you can write out the two equations that explain the corrosion of iron. Well, it's Fe changes into Fe2 plus and 2 electrons. And then we've got Fe2 plus changes into Fe3 plus and an extra electron. Where the pink comes from in the diagram involves this equation here. Remember that rusting from a previous lesson requires oxygen and water. So there's your oxygen and your water. So we have an ion electron equation where we've got oxygen and water. And when oxygen and water react with 4 electrons, it becomes 4OH minus. Now, I can appreciate that's quite hard to remember. So please, just don't worry about it. If you look at page 10 in your data booklet, there is only one equation that has water and oxygen reacting. And it's written, I believe, as is written on this screen. So you can just write it down from that page. Now, so how this works is, where does the pink come from? Well, just to clarify one more time first, that the ferroxyl turns blue in the presence of Fe2. So here, ferroxyl turns blue. Ferroxyl it stays clear, stays yellow here, it's blue here because that's Fe2, and here it remains the blue colour because it's already reacted. So ferroxyl turns blue in the presence of Fe2. Ferroxyl, as it contains the indicator phenolphthalein, ferroxyl or phenolphthalein turns pink in the presence of OH minus. Now, when I have done this experiment in class, we never see the pink colour by using ferroxyl indicator. Now, the reason for that is blue is such a darker colour and a deeper colour, and perhaps there is more ions of Fe2 plus produced. So therefore, the blue masks the pink colour, so you can't see it anymore. So, if you were to do this experiment with ferroxyl indicator only, then ferroxyl indicator in the bottle is clear. And it's clear when it's near neutral or acidic, but it turns pink when the pH is greater than 8. So we are talking about alkaline solutions. As rusting produces OH minus, this increases the concentration of OH minus ions and so therefore makes the solution more alkaline. And the more alkaline the solution is, the more pink you see. So that is why ferroxyl indicator could, in theory, turn pink, because OH minus are being produced. Now here's a little diagram that you're going to see in the future topics about acids and alkalines. When something is acidic, there is more H pluses than OH minus. When something is neutral, that means there is a balance of H plus and OH minus concentration, and this is the situation we're talking about just now. So we had originally the water, which was neutral, but during rusting, OH minus was being produced, and so therefore the solution became more alkaline, causing the phenolphthalein to change from clear to pink. So in summary, ferroxyl turns from yellow-green to blue in the presence of Fe2. If you remember the start of the story, the end of the story, and the above fact, you should be able to write the ion electron equations for iron, which is at the start, changing into Fe3 plus, but going through that Fe2 plus intermediate. Of course, you can copy all equations from page 10, however I recommend only copying down the water equation from page 10 of the data booklet. It will enrich your understanding of the chemistry. Phenolphthalein changes from clear to alkaline as OH minus ions are produced, during rusting. So thank you for watching today, and if you need any help or support, please get in touch. Like and subscribe.